Today we're going to take electromagnetism to the next level where we're going to talk about the fact that it is light. And we're going to talk about the entire electromagnetic spectrum. Right, so let's start off just the basics about light. So the first thing is there's a little bit of confusion here, right? That the word light is used interchangeably with the electromagnetic spectrum as a whole, but really it's light technically refers to the part that we can see, that we're sensitive to with our eyes, and so that's just a tiny sliver in the electromagnetic spectrum, which is what I'm going to be talking to you about today. Um, it's all really the same thing. It's just, of course, we have our own biases, right? Because we see certain frequencies of light, and we think those are super important. And historically, we didn't even know these other phenomena were just different colors of light, basically. So what is it made out of? Well, you had the big reveal last time. Maxwell is the one who figured this out, basically mathematically, by thinking about Faraday's law of induction and adding a symmetric counterpoint where changing magnetic fields create electric fields, and changing electric fields make magnetic fields. And what he derived mathematically is that you actually can get the formula from a wave out of these electrical and magnetic equations if there was a source charge that was accelerating, right? And so you have this. These fields don't need anything else in order to propagate. Like a sound wave needs like air molecules or something like that, or the wave on an ocean needs the water. What's so cool about electromagnetic radiation is it's the fields inspiring the fields, right? And the oscillation is just there. Um, Now, there's two ways to think about this radiation as it travels through space from the source, which is that accelerating charge. You can think of it as being made out of particles. That's the photon model, and that's really useful if you are looking at like a single electron or something like that, or a single charge that just does a short, sharp acceleration and then stops, right? So kind of like in chemistry class, you might talk about an electron changing orbits and emitting a photon of a precise frequency as it falls from a high orbit to a low orbit, right? And so that's a situation where it kind of makes sense to look at it like a particle. But today we're going to be talking about wave, right? So if you have like a continuous source, like constantly accelerating particles, and then they're just constantly churning out the signal, we can talk about it as a wave, right? And this is a way to picture the wave, what's going up and down. Now, this is a little bit misleading, this diagram. There's actually nothing physically extending up and down or left to right. What we're showing you here, and what all the books show you, is a graph of the strength of the electric field and the magnetic field, right? So we've got the electric field and the magnetic field. They're both at right angles to each other, and they peak out simultaneously, and then they go down together, and then, right, because one is triggering the other one, and then they're traveling through space. Now, what's happening, right, is that the electric field strength, as you go through space like this, is getting positive and stronger, and then positive and weaker, and then falls to zero, and then gets negative and a bigger negative number, and then a smaller negative number, and then zero, and then bigger. So when you see this wave here that looks like an ocean wave or a wave on a string, it's a little bit misleading, right? Because the light is actually not going up and down. The light is just going in a straight path. But what's happening here is the values of the light, right? When you graph them, you get this up and down pattern. Both the magnetic and the electric field, right? You can't have one without the other in order for the radiation, because remember, it is the changing of one that triggers the changing of the other. Now, what determines the shape here? So there's several different descriptions here. We're going to elaborate a little bit later. But the most important attribute is how fast and furious these peaks come, right? Which you can describe in a couple of different ways. One would be the wavelength, that is how far you have to travel through space to go from one peak to the next. And the other one would be the frequency, that is how many times these things go up and down per second. And that is determined by the source, of course, and it is determined specifically by the energy that the source is using when it's accelerating, right? Now, once the electromagnetic radiation is released, then it travels and propagates through space at a value that was derived by Maxwell, and of course corresponded to the experimentally determined speed of light. But Maxwell showed with math that it is determined by the electric force constant and the magnetic force constant, right? There's a function, and you can actually derive it from the equations that describe electricity and magnetism. So when people ask, why is the speed of light what it is? Why is it this big number, 300 million meters per second? It's because it comes from the K value in Coulomb's law and the mu value in the magnetism equation. So those constants actually do change somewhat depending on the charges that are in the material, right? So the values that we used in class and the value that gives this 3 times 10 to the 8th, this famous speed of light in a vacuum, such a famous number, it gets its own letter, C. That all those values are quoted for empty space, right? A vacuum where there's nothing, there's no charges. Generally speaking, if you start putting things in there like air molecules or um, water, if it has to travel through water or if it has to travel through glass, right? Those are increasing the amount of charge per cubic centimeter, and that will slow the radiation down, right? You're an electric or magnetic field. You're going to zip along super fast if there's no charges to slow you down, and it's not exactly correct, but more or less, the more charges you encounter, the slower you're going to go. So the speed of light, the quoted number is in empty space, and then it goes a little bit slower when it hits a gas, like say the atmosphere, and then even slower when it gets into water. So for instance, the speed of light in water is about 30% slower than it is in outer space. And then slowest of all, of course, in a solid like glass or some kind of transparent solid. All right, I think I already talked a little bit about this, but here's some of the, if you take a snapshot of a wave, this is general wave vocabulary, right? You could talk about the distance from peak to peak, or the distance from trough to trough, or the distance for one complete cycle. You'd measure that in meters. That's the wavelength. The peaks are sometimes called the crests, and the minimums are called the troughs. Um, and of course, what is radiation in general is the transfer of energy from one spot to another. All right, now the other attribute here that is related to the source is the amplitude. That is how strong of a signal we have, right? So the energy of the individual charges accelerating determines the wavelength and the frequency. And then how many of those are happening per second? In other words, the overall brightness of the source. Do you have a million electrons that are undergoing this acceleration or just one? That'll determine the amplitude, right? Which would basically correspond to how bright the light is, right? The fact that you have a certain energy source is giving you blue light or red light or infrared light. And then how bright the blue light is or the red light is or the infrared light is determined by how many objects, how many charges are accelerating at the source. So here's the whole spectrum. It's a great synthesis of a lot of things that had been experimentally observed by the time Maxwell came up with his equations in the late 1800s. But people really didn't know that it was all just the same phenomena. And that's why you have all these different names. And to this day, people think of them as very different phenomena, but they are all electromagnetic radiation. And the only thing that's different between a gamma ray or an ultraviolet ray or the color green or a radio wave is this frequency, right? It's just the acceleration value of the charges producing it. The lowest energy, least accelerating charges have the longest wavelength, and that whole regime is called the radio waves, right? So the longest wavelength is what we have named radio waves, and that, of course, is where the radio frequencies are for radio stations and things like that. Then as you sweep up, you've got the microwave region is slightly shorter wavelengths, but still pretty long compared to visible light. And this is indeed where the microwave ovens are and all that kind of stuff. And this is where your Wi-Fi is and stuff like that. Infrared, this is the kind of radiation that you can feel that's coming off of something that's hot, but you can't see it with your eyes, although there are some animals that have night vision that have evolved to see in infrared. It helps them hunt because they can see other animals' body heat coming off of them in the night. And then we've got the part that's so important to human beings. This is not to scale, right? The whole visible spectrum is a tiny, tiny sliver. This is this entire graph here is is a logarithmic scale, as you can tell by these numbers down here, and they're not to scale. Radio and gamma are the largest by far. basically the way this works is as you get further and further from what humans can see, the bins get bigger and bigger, right? So visible light is a tiny sliver. All the colors of the rainbow that humans can see is hardly any width at all in the spectrum. And then ultraviolet and infrared are the next biggest ones. And then microwave is quite a bit bigger, and X-ray is quite a bit bigger. And then, gamma ray theoretically goes all the way out to infinite frequency, and radio waves theoretically go all the way down to zero frequency. So let's just run through and talk a little bit about these various things. So we'll go from high to low. So the highest frequency are gamma rays. Notice the term rays here, right? When they were discovered, people had no idea that they could even be modeled as a wave, that they were like visible light or anything like that. And they were named in the early days of detecting radiation, and that's why things like the helium nucleus isn't called the helium nucleus, it's called the alpha particle. A free electron is not called a free electron, it's called a beta particle. And these high energy, high frequency light rays aren't even called light rays or electromagnetic radiation, they're called gamma particles. And eventually, through careful experimentation, people figured out what these unknown radiation particles were that were coming out of radioactive isotopes, right? So gamma rays generally are, they're being emitted by a very high energy, unstable nucleus that's falling to a lower energy state. There are other sources of gamma rays, but that would be the most common one on Earth. That's everything that is higher frequency than visible light, from the upper bands of ultraviolet all the way up, is considered ionizing radiation, right? So somewhere in the middle of this UV range to the right, all of that is considered ionizing radiation because the light frequency is high enough so that the individual photons have enough energy that they can actually knock an electron right out of a molecule, right? And then it becomes an ion, hence the term ionization. And of course, if you change the charge of a biologically active molecule, you will change its functionality, right? And so generally everything from UV up is considered biologically harmful. And on the other hand, everything below that is non-ionizing, meaning that they don't have enough energy to actually knock an electron out of a biological molecule. So the most they can do is heat up stuff, right? Like a microwave will heat up your food, or infrared will heat up your food, but they will not actually sort of mess with the chemistry of the object. So still high frequency and still dangerous, was discovered much earlier, before gamma rays. Once again, didn't know what they were looking at the time, called them X-rays, right? X because they were mysterious. And of course, this is what happens when when you want to image your bones and stuff like that, they'll take an X-ray. Because it is high enough energy to penetrate through the soft flesh, but will get stopped by a hard bone, or you can see this person's wearing a ring on their finger. Then you're down to ultraviolet, right? So ultraviolet, the upper frequencies of ultraviolet do cause damage to the cells. So here's a mechanism by which you are basically increasing your chances of skin cancer when you get a tan with the UV, is because an incoming UV photon may hit a strand of DNA. If it did, it would ionize that strand, which would then change the conformation of the DNA molecule, which would change how it gets transcripted. And that's one of the models by which a cell can become a cancerous cell. Now here is the part of the spectrum that we know and love the most, but look at how narrow these regions are, right? So the colors that you learn from the rainbow, they stack that way because they're stacking in order of frequency. And that's why they're always in the same sequence in the rainbow. And you go from red to orange all the way up to the blue and the violet end of the spectrum. You're going from low frequency to high frequency. And these are the smallest bins on the entire electromagnetic spectrum. Now, I have a slide about this later, so I'll talk about it when I get there. But it's interesting to note, like, why are these bins, right? The fact of the matter is that the radiation out there in the universe is continuous, right? You can get any wavelength of electromagnetic radiation. So why is it that our eyes only see certain colors? We can't actually tell the difference between, say, 630 nanometers and 650 nanometers. It all just gets glommed into red. Now I'll talk about that in a minute. The answer, the spoiler is it's biological, not physical, not physics related. So going just below red, infrared is so, like I said earlier, some animals have adapted to see this, but this is the frequency that's emitted by mammals and warm-blooded objects. Um, Something I didn't mention before is that everything that has a temperature, uh, of course, is in thermal motion, right? Is in some kind of motion, and so um, molecules and atoms have charges within them. If those charges are vibrating, then they're accelerating, and that means that everything that has temperature in the universe is actually emitting some electromagnetic radiation. You, as you're sitting here listening to this, right? Your body has some thermal energy, and so every single atom in there is kind of randomly vibrating back and forth, and it is emitting, and it turns out that that energy level is about comparable to the infrared, which is why people can feel your body heat when they stand next to you. Things that are colder are going to emit at the lower end, right? So let me go back to here we go. If you look at the very bottom here, you got temperature of body emitting the radiation, right? So this is in Kelvin. So absolute zero would, of course, emit no radiation at all, but low temperature objects will naturally emit radio waves, and super high temperature objects will naturally emit gamma rays. Right? There are other ways to get the radiation, but just this is my point, is about the temperatures down here corresponding to certain natural radiation, and people use that. Astronomers use that all the time to infer things about the source. Going above infrared, you get to below, right? We're going to lower frequency, longer wavelengths. We're getting into the microwave region. It's kind of a one-off that microwave ovens are so good at heating up food. It's because there's a specific frequency that water molecules will absorb. I think it's a rotational mode of the H2O molecule, and that frequency is highly absorbed by water molecules, and of course gets them into motion, and which is a great way to heat up food. When you go to a restaurant and they serve something early and they want to keep it hot, they'll put it underneath an infrared lamp, which will bleed over into the red, so you can see that it's on and you'll see the red light, but it's really the infrared part that you're not seeing that's keeping the food hot. And then even lower is the radio wave, which is a huge band, right? Which all of we harness for communications all over the place. And so that's your tour through the electromagnetic spectrum. And I only want to talk about one other thing, which is why we only see certain discrete colors, right? And the reason for that is because at some point our eyes have to capture the energy from the light coming into our eyes and convert it into a signal that our brain can use. And the mechanism by which we do that, it turns out, is only three different biological molecules in the back of your eye and the retina. They are the three cones, the so-called red, green, and blue cones. And these are the frequency ranges over which those proteins are biologically active, right? So your blue cone will get triggered to various degrees, will get triggered really hard at the peak and less at the edges by these wavelengths. The green is responsive to these, and then the red over here. And since these are the only three that we have, we can only interpolate, say, 1, 2, 3, 4, 5, 6, 6 or 7 bands of color, because we're only getting signals from these three different molecules. And this is the reason why in computer programming or in art you can recreate the entire color palette from only three primary colors, right? That's not a physics thing. It's that we're taking advantage of the fact that we're biologically limited to actually, out of the continuous spectrum, we're only getting these three signals, right? So if you press on these three buttons in various combinations, you can fool a human being into thinking they see the whole color. And an alien that had evolved different sort of sensory apparatus would come in and look at one of our TV shows or a painting that had been used from only three primary colors, and they would not agree with you about what color the actual object is. Okay, so that's your whirlwind tour of this electromagnetic spectrum, which is a really, of course, powerful concept in science. Thanks.